Hello, everybody. Thank you for coming to the third lesson. Today we will cover, Today we will cover in part one, uncorrelated network and structural cutoff and measure of correlations. So what do we mean by degree correlation? What are uncorrelated networks? And this will be a more of an empirical part with tips on how to analyze real data sets, so how to do network analysis and check for degree correlations. And in part two, I will expand more about canonical network ensemble with a given expected degree sequence. And I will show how these canonical network ensemble have degree correlation, but how we can, how we can reduce them to describe uncorrelated network if we introduce what is called a structural cutoff, so a maximum degree for the node. So if the networks are sparse enough, they can become uncorrelated. And then I will tell you more about microcanonical network ensemble, in particular the configuration model, and I will expand on non-equivalence of the ensemble. But this will be in part two. So we start with part one, and first of all, the references. In the first part, I will have quite original accounting of description of what do we mean by degree correlation. Some of this is in the Mark Newman book, which has worked extensively on that, but is not exactly following the book. And then for the rest of the session, I will cover quite extensively these two papers of myself with Kartik Anand in 2009 and in 2010. So let's start with this part one and discuss what are correlated and uncorrelated networks. And here with correlation, I will refer always to degree correlations. So when we speak about degree correlation, we take the point of view of the links, okay? And we ask whether a link is connected to two nodes that have correlated degree. So whether the probability that the links connect to a node of degree k depends on the degree of the other node at the other end of the links. I will be more specific, but this is the sense. So first, I will describe uncorrelated and correlated networks in terms of degree classes. So where I consider, the nodes that have the same degree as one class. So I will, so first of all, let's find out one of the main quantity when describing a network, when doing dynamical model on the network. And this quantity is the probability that the random links connect a node of degree k. And this probability, Q of k, also called excess degree, this is equal to k pk, where pk is the degree distribution of the network divided k average. So as you see, this probability is not equal to the degree distribution and is biased toward nodes that have high degree. So if the degree of the node of a node is much higher than the average degree, then this excess degree is much larger than the degree distribution associated to the value k. So how can we find this expression? Well, it's easy. We are asking whether what is the probability that a random link is connected to a node of degree k. So in the network, there are nk equal npk node of degree k, and each of these nodes is connected to k links. So the probability qk should be proportional to k n of k, and we normalize. So then n of k is nothing else than n multiplied by p of k. We can simplify n and we get this expression. This is very important because practically I tell you that if you sample the node of the network just randomly, you take a node randomly, you will choose a node of degree k with probability pk. If you sample the node of the network by considering the node at the end of the link, you will end up biasing the distribution toward node of high degree. And this has a lot of important consequences, including the fact that in social network, there is this friendship paradox, and in average, your friends have more friends than you do. This very interesting paradox that has a number of consequences. So now, if we want to calculate the probability that a random link connect a node of degree k and k prime, in a network, we can construct a matrix ek k prime, and we construct by looking at each link separately and updating ek k prime by adding a 1 for k prime and adding another one into the entry k prime k. Okay, so notice that if the two connected nodes have the same degree, you will add 2 to this class EKK. So you have this probability that a random link connect two nodes of the k and k prime is just equal by this matrix that you have been constructing divided twice the number of links, because in this matrix you count you are doing a kind of histogram of each end node of the link. So this twice, then each link is counted twice, so it's twice the number of links, and is the average degree n. And of course, the probability that the random links connect to a node of degree k is the marginal. So you need to sum over k prime, and you get pi of k prime, and you get q of k. Okay, very good. So in order to define uncorrelated network, we want to determine the conditional probability that a link is connected to a node of degree k, given that the other end of the link is connected to a node of degree k prime. And this is just determined by Bayes' rule. You have P of k prime, so the probability that the link is connected to k and k prime, divided q of k prime, so the marginal probability that one end is connected to k prime. So this is the probability, that the link is connected to a degree k, given that in the other end is connected to a degree k prime. So an uncorrelated network is a network in which this conditional probability is independent on k prime. So if I follow a link, I have, and departing from a link of degree k prime, I have always the same probability to reach a node of degree k in an uncorrelated network, while this is not true if the network is correlated. So in an uncorrelated network, this pk k prime can be expressed as the product of q of k prime. Okay. So what does it mean for network analysis? How can we detect and evaluate the significance of degree correlation? What is their meaning in a real network data set? So the degree correlation, again, I'm repeating a little bit myself, are a network has degree correlation if the probability that the random link is connected to a node of degree k depends on the degree k prime at the other end of the link. So the conditional probability pk k prime also depends on k prime. So what happens is that we can classify degree correlation in two big classes. The network which have display assortative correlation, which are called assortative networks, and networks in which that display disassortative correlation and are called disassortative networks. And if the degree can vary quite widely, in assortative networks, essentially you have high degree nodes that are more likely to be connected with high degree node. This is something that happens, for instance, in social network where social hubs are friends of each other more than in a null hypothesis. And the opposite is this assortative network in which hubs are more likely to be connected to low degree nodes. And this happens, for instance, in biological networks. It happens in also technological networks. So an example of assortative networks are social networks and protein interaction networks. An example of these assortative networks are technological networks. So how can we measure this degree correlation? So the first thing, if we have enough statistics, we can directly measure p, k, k prime and check whether it is factorized into two contribution qk and qk prime, or whether in a null hypothesis we get something consistent with what we observe in reality. But this method has some limitation. In particular, you have to construct this matrix pk prime, and you might have few data for each bin. So what you want to do, you may want to take maybe bins that are not just one degree and another degree, but you want to have, logarithmic bin size on the degrees or something like that to increase the statistics in for each entry of the matrix. And another thing is that you want to have a null model to compare with an uncorrelated ensemble. So what you can do is, what is done in practice actually is to use this swap of connection algorithm. So you choose two random links with connected to four distinct nodes. And if possible, so if there are no, the move is meaningful, you swap the links. Okay, so in this way you preserve the degree of the nodes, but you change the degree correlations because you change, both for each links you change the pair of node connected at the end of the links. And what you can do is you can compare the real degree correlation with the degree correlation that you get after this randomization process. And this is what is done in this paper by Maslow and Snepren. And here you see these data sets contain disassortative correlation, because you have practically here high degree on one side connected to low degree on the other side. And this was it was the first paper where this technique was proposed. So you can have this full matrix, and then you practically map this ratio between what you observe and the null model given by this swapping algorithm. There is an alternative way to look at correlation, in particular if you don't have enough statistics in this matrix. Each entry can be quite few. You could have very few data in some of these entry of this matrix. So you want to have a more constrained measure. And in that case, a very powerful method is to consider the average degree of the neighbor of a node. So you look at all the neighbor J of the node connected by the adjacency matrix Aij, that is equal to 1 for each of the neighbor, and you sum their degree and you do the average. So you are asking what is the average degree of the neighbor of node I, and you can bin this into node of degree k. So you can ask yourself what is the average degree of a node that has degree k in the network. And then the idea is to look if this is a function that is increasing with the degree or decreasing with the degree. And there are some comments. So this is a technique which is better respect to the one of the matrix in the sense if you have low statistics of degree classes. But still here you are looking for monotonicity of this function k and n of k. So you want to know if you have high degree, if your friend also have in average higher degree than compared to a node that have low degree, that maybe their friend have in average lower degree, okay? Or so you want to know if this function is increasing or if this function is decreasing. So if you want to capture the opposite trend. But sometimes these functions are neither increasing nor decreasing. So this function might be, more complex. So the understanding and interpretation of this method is less transparent. And so in that case, you need even a more constrained measure of degree correlation. So in the good scenario, in the best hypothesis, you might want to have this function, the average degree of the neighbor of the node of degree k, plotted versus k in a log-log plot. And if this is a increasing function, so if the node of high degree has in average friends that have higher degree than a node with low degree, the network is assortative. If the opposite is true, so the node with high degree has in average friends with lower degree than the node with lower degree, then the network is a disassortative network. And this is the case. For instance, here you see these dots. This is the autonomous system, the internet at autonomous system level. It's one of the first paper by the group of Vespignani looking at this. They found that the correlation are clearly disassortative, and this is a quite general trend in technological network. And this is not captured by a number of methods, including the Barabasi-Albert model, but is included, for instance, in this model which we propose with Barabasi and myself, which was called originally the fitness model, and now it's more popular, call it Bianconi-Barabasi model. So there are different models, and different models can capture different level of correlation, and the idea is to try to find the best model that capture the essential correlation in a real data set. So but I mentioned that this technique might be still quite can have some problems, because you might have a function that is not really monotonic, and in that case you would need a even more coarse-grained measure of correlation, and this is what has been proposed by Newman, correlation coefficient, which practically measure for each link, essentially, for each pair of nodes, sorry, of degree classes k and k prime, whether this pi k prime differs from the uncorrelated expression. Okay, so if R is positive, then you expect a sortative network. If R is negative, then you measure a disassortative network. And here you have a single number. You know, the first method we had a matrix. The second method we had essentially a vector, a line. Here we have a single number that characterize the degree correlation. So this is at a increasing level of coarse-graining over the network. So now we can ask ourselves, how can we model degree correlation at the level of the node, with using the node label, and we can start with uncorrelated network. In uncorrelated network, if we have each node I as an expected degree k bar I, then the probability that a random link connect node I and node j is given by bar ki bar kj over k average n to the square. Okay, and so this is the definition of having uncorrelated network here, assuming with this assuming that we describe this this matrix ij, the pi ij at the node level. So of course, we might want to ask, what is the probability that the random link connects exactly to a node I? And this is equal to Qi, which is k average In over k average n. And in an uncorrelated network, what we have is that the conditional probability that a random link connect to a node I, given that the other end is connected to a node J, is independent on the node J and is only given by this expression, Qi. So we are in some sense translating what we have done with the degree classes now at the level of the node label. So if we want to prove that, we have this general expression Pij for uncorrelated networks, and we want to show that for uncorrelated network, the conditional probability that the random link connects to a node I, given that the other end is connected to a code J, is just given by Qi. So we can define this conditional probability with Bayes' rule. So it will be pi ij divided by the marginal that the random link is connected to a node J. And if we look at this denominator, we insert the definition of Pj prime, we sum over j prime, and we get essentially this expression. Now, inserting this here, we in the definition of pi I conditioned on j, we find the result that we want to find. Okay, so we have the definition of pi ij, and then this normalization, this marginal that we have calculated here, and we get Qi. So is this probability that a link connects to a node I is independent on the node J at the other end. Okay, if I follow a link, I have, starting from any node, I have always the same probability to end up to a node I. So here, this is an example. So this is the probability pi ij, and practically, the probability that pi ij is given by practically two contribution, qi and qj, and qi here will be 2 because this node has degree, expected degree 2, divided this k average n, and here the other end as probability 3 divided the number of stubs in the network. Okay, so this pi ij is the product of these two terms that are independent one from the other one. Sorry. Yes, so now we can ask ourselves something a little bit different. So what is the probability that I connects to J? So it's not the probability that a random link connects I to J, but what is the probability that by considering all the links, I is connected to J? So what we can do is we just calculate this probability Pij, and what we can do, we can start with pi ij, the probability that a link connects node I and j. We multiply by the number of term that we need to consider the link, because the link can connect I and j and I, so it's 2L, and we get this that will be the, essentially, if we place link randomly on the network with probability pi ij, will be the expected number of links that connect I and j, because I might assume that I can end up with two links connecting to node I and j. And since I make the assumption that actually the network that I'm studying is simple, I practically say that multi-links are not possible. So this expected number of links between node I and j is nothing else than the probability that the link is there. So because I assume, I enforce now that Nij can be, should be, so that the number of links connecting I and j should be either 0 or 1. Okay, so this is an assumption that I do that I need to, in some sense, control. Okay, and so in order to understand this expression, Pij is now Ki Kj over K average n. I don't have any more the power 2 here. So in order to understand this expression, the probability that I connects to J is the probability that this end connects to J. So it's 3 over K average n. I choose these 3 stubs out of all the stubs possible that I can match this link to, and I multiply by 2 because here I need, it is possible that these stubs connects to J or the other stubs connect to J, so I need to multiply by 2. Okay, so this is the interpretation of this probability that I connects to J in an uncorrelated network. So now, as I mentioned, the fact that I'm assuming that the network is a simple network is something I need to control, and this expression that I use for Pij, the probability that I connects to J, can be valid only if the network is sparse enough. So only if the maximum degree in the network is smaller than this structural cutoff that goes like the square root of the average degree multiplied by n, meaning that I cannot have a largest degree that is arbitrarily large. So the maximum degree in a network of n node can be n minus 1. But in order to have an uncorrelated network, I need to impose instead that the maximum degree should be smaller than the structural cutoff. So smaller than something if the average degree is constant, something that grows like square root of n, not like n. So why is that? Well, because one thing that I want to make sure is that this is a real probability and is not an average number of links that can be greater than 1. And in order for Pij to be a probability, I need to impose that this quantity should be smaller or equal than 1. Okay. So, how can I be guaranteed that this is true? Well, I substitute Ki and Kj with the maximum degree of the network, and I still need to have something that is smaller or equal than 1, because I want to define the probability that this I and j, which both have the highest degree of the network, are connected. So if this should be smaller or equal than 1, I see immediately that the maximum degree of the network should be smaller or equal than the structural cutoff. So actually, what happens if I have a network without the structural cutoff, I want to try to construct uncorrelated network, I might end up very likely with multi-edge. Okay, so, and if I want to avoid multi-edge, I will add correlation. So, and this is essentially what happens. So for instance, for scale-free graph, you can define what is called a natural cutoff. So the largest, the scale of the largest degree, given that you impose that the degree distribution is power law. And this natural cutoff grows like n to the 1 over gamma minus 1. So you see if gamma is equal to 3, this is 1/2. So consistent with the structural cutoff. But if gamma is less than 3, and this is the case of scale-free graph, which have very wide degree distribution, large hubs and things like that, then this natural cutoff is higher than 1 over square root of 2. And so what if I want to construct a network with this degree distribution, naturally I will not satisfy the structural cutoff. So yes, so this natural cutoff for the scale-free distribution is much higher than the structural cutoff for gamma smaller or equal than 3, meaning that scale-free graph tend to have very high degree, much higher than this bound that is the structural cutoff. So if I want to construct an uncorrelated network, I need to impose by end that my scale-free graph has a degree that is not higher than something multiplied by n to 1/2. And so only in that case I can get a network that doesn't have degree correlation. Okay, so this is concluded the first part. And then in the second part, we will see how practically when I want to construct a canonical network ensemble with a given degree sequence, I have two possibilities. Either my degree sequence doesn't satisfy the natural cutoff, and then the network that I'm generating has some correlation, which are called natural correlation, due to the fact that they have this large cutoff, or my degree sequence obey the structural cutoff, and then I will generate an uncorrelated network. So it's very interesting if you practically, if you want to have a maximum entropy ensemble with a given degree distribution, if you don't impose the structural cutoff, you might end up with something that is correlated. And this is due to the fact that you practically want to match these stubs, and you have node of very high degree and several nodes with few degree, and you want to avoid multi-edge. And in order to avoid multi-edge, you practically build up disassociative correlation. So the nodes of high degree will link more likely to node of low degree if you don't have the structural cutoff. So in this first part of this class, we have covered correlated and uncorrelated network. We have discussed measure how to calculate the degree correlation in network. And then in the next part of this lesson, we will see how this classification can help us understanding better the canonical network ensemble, and how we can also study the microcanonical network ensemble, and how can we expand on the non-equivalence of the ensemble. So let me finish this class here and stop the recording.